this topic, modeling with zeros, which we find on slide 16, an overview. And this is our way of orienting you where we are in this sequence of advantages of growth modeling in a latent variable framework. We've worked our way down these bullets, and we're not now at the exciting spot of modeling of zeros. So now we're going to put together several of the building blocks that we talked about yesterday and that you mastered fully at this point. And we're going to talk about modeling with the preponderance of zeros, as it has been called in the literature. And we're going to make a distinction between two, we're going to focus on non-normal data. Non-normal data, and we're going to make a distinction between two cases, the one on the left and the one on the right. So on the left we have 5 different categories. It could be a so-called Likert scale or Likert scale, scored from 0 to 4 or 1 through 5. And it looks a little non-normal. But on the right, we have the situation where it's not only non-normal, but you have a strong floor effect where you have, looks like more than 50% in the, at the lowest value. So it's like the full, we don't know whether or not all of these people are the same. If you change the question wording somewhat, we may have been able to spread them out. So it's like we have a floor effect here, and that's a very special variable that needs special attention. For variables on the left, like on the left here, you can actually treat those variables as continuous and apply an estimator like maximum likelihood. And although maximum likelihood assumes normality for continuous variables typically, the point estimates will be quite good even when the distributions look like that. But you do have to correct the standard errors and the chi-square for non-normality. If you have non-normal data like this and you ignore it, the regular standard errors are going to be too small. So you're going to have significant effects, more often significant disease tests than you should. So ignoring non-normality, using normal theory techniques, you have too small standard errors, and then the opposite for chi-square, you have too large chi-squares. So you would reject a model that's not necessarily wrong, but just is a model for non-normal data. That's okay for this kind of distribution. I would use then MLM or MLR as the two estimators. But on the right, you have a situation that where already the point estimates would be off. The standard model, which are linear models for continuous variables, the standard linear models are not appropriate when data are of this kind. The assumptions are likely not to hold, and you will get biased point estimates. So that happens for continuous data, and very often happens for a special kind of outcome, namely a count outcome. So when the values are actually integer values, 0, 1, 2, 3, 4. How many times in the last 30 days did you do this or that, for instance? So it's a count variable, and there are special modeling techniques to take into account the high preponderance of zeros in that case. And you can also take a categorical variable approach, where this is an ordered polynomous or an ordinal variable. But sometimes you have so many different distinct values that you would, it's better to treat it as either a count variable or a continuous variable that is perhaps censored. Censored meaning that it cannot assume values less than 0 in this case. And so there's special censored normal modeling, and in regression analysis that's been called Tobit regression. But that kind of modeling is available to us in M+ for all kinds of situations, be it factor analysis or growth modeling. We're going to focus quite a lot on two-part modeling, or semi-continuous modeling. which there was an interesting article in JASA by Olson and Schaefer, JASA being Journal of the American Statistical Association, doing a longitudinal version of an earlier paper by Naihua Duan and others at the RAND Corporation in Santa Monica, where they dealt with data that looked like this, and they created a so-called two-part model for data of this kind, not focusing on counts, but a continuous variable that can assume values, not only the integer values, but has that preponderance of zeros. We also have a mixture model possibility here. For instance, if you work with counts, we have a very common mixture model that's called zero-inflated Poisson. And we're going to talk about that here this morning. It has a flavor of, part of that is a Poisson model, part is a logistic model, like we talked about at the end of yesterday. And there are other kinds of mixture models that we will talk about in August. Let's see. Let me show you these in terms of pictures here. Here's two-part modeling. Two-part modeling starts with a variable that looks like this. You know, that's kind of data that you don't want to show anybody that you have. They look much too skewed, and you can't even pretend that it is normal. But now you don't have to be ashamed anymore. These data can come out of the drawer, and you simply create two variables from this variable. One variable says, are you at 0 or are you not at 0? So here are the people who have 1, 2, 3, 4. That's one variable. It's a dichotomous or a binary variable. And for those who are in 1, 2, 3, and 4, you actually have a variable with those values as a continuous variable, in this case. So a variable that doesn't have the value 0, but goes from 1, 2, 3, 4, and up. So you can think of this as, if you take an NIAAA example, alcohol example, and we do that because we have been funded by NIAAA many times, many years. It could be frequency of heavy drinking in the last 30 days. So did you engage in heavy drinking or not? Not. And those who did. And if you did, how many times in the last 30 days did you engage in heavy drinking? Once, twice, 3, 4, etc. So that can then be represented as a parallel process growth model. So you have the binary part down here. So the U's in M plus notation are categorical variables, in this case dichotomous, binary. And you have a growth model, say a linear growth model for that development, the development of the probabilities over time. And then for those who have engaged in heavy drinking, you have a growth model for the amount of heavy drinking over time. This could be years, for instance. And if you arrange your data like this, you can do a parallel process growth model, and Linda's going to talk about an example, talk about exactly how these variables are dealt with. Now, another model that we're going to learn about is the inflated growth model, and this happens then for count outcomes. And at this point, we're not going to even try to understand this diagram, but in essence, it is also so this could be a zip modeling, for instance, zip being zero-inflated Poisson for count outcomes. But it also leads to a two-part model, but where one part is a latent binary variable, as I will explain shortly. An interesting situation that I don't think has been fully explored statistically yet, and it'd be fun to do that, is one where you have a lot of skewness like this, a lot of skewness in your data, a lot of strong floor effect, due to the fact that at a certain age, in a certain grade, for instance, a large proportion of your subjects have not yet started to engage in the activity. So like heavy drinking, for instance, in grade 8 or something like that. So you, at a certain point, then you're going to have a lot of people at 0. But then suddenly you come to a grade or an age where they start experimenting with that, and you have a growth model for the amount or for the frequency that they engage in that activity. So that then leads to what we're going to talk about this afternoon. You could have a survival model for onset of engaging in this activity. Time to onset of this activity. And once the onset has started, what's the growth curve for that? So it's a combined survival and growth model. And that I don't think we master enough. You have the article here, Albert and Xi, but that's in biostatistics or biometrics, and it's for cluster data. I think it's mice, so it's not quite applicable. And there are special difficulties for behavioral data, because the definition of onset, although that's relatively straightforward when you're talking about tumor growth in mice, has a tumor started growing or not, it might be harder to define what onset is in behavioral studies. What constitutes starting to drink or starting to smoke? How much? What should define drinking regularly? You know, it's not clear cut what the limits or threshold should be. So onset in some way has a measurement error, which is an interesting modeling twist. Anyway, so this is a little bit of an overview and a look ahead to what we're going to talk about. Here you have two-part growth modeling, and I think that looks very applied and practical, so that must be Linda.
Probably.
Can't possibly be me.
Thank you. Okay, so now we're going to look at an example of two-part growth modeling, and we're going to be using the AMPS data, and these are data taken from the alcohol misuse prevention study, where there were 49 schools with approximately about 2,666 students who participated, and they were measured 7 times. What we're looking at, though, is just a small subset of the variables in that data set, and we're looking for 3 items related to alcohol misuse. The items are, during the past 12 months, how many times did you drink more than you planned to, feel sick to your stomach after drinking, get very drunk? And then we take the average of those 3 items is what we'll be looking at. And we'll be looking at 4 time points: fall grade 6, spring grade 6, spring grade 7, spring grade 8. And after yesterday, you should think non-equidistant time points. So that gives you your clue for your time scores there. So here's what the model looks like overall. We have 4 measurement occasions, the average drinking at time 1, 2, 3, and 4. And then we have the intercept growth factor, slope growth factor, so just similar to what we looked at yesterday. Now, this is the original variable. We're going to look at this as a 2-part model, so we're going to have to create the 2 variables from the original variable. So we show you here how this is done. And M+ actually has a data 2-part function which will divide the variable into 2 variables for you. So if the original variable, which is called AMOver, is greater than 0, then the binary variable, which we're going to call U, is going to take on the value 1, and the continuous variable, which we're going to call Y, is going to be the log of m over. If the original variable is 0, then u will be 0 and y will be missing. And if the original variable is missing, both variables u and y will be missing. We take the log. Olson and Schaefer recommend that. M+ does that automatically for you in data 2 part, and also allows you to do no transformation or to do other transformations of that variable. So we'll leave, well, maybe we won't leave that there. Okay, so let's take a look at what the model that we're going to estimate looks like. It has the u part of the model down at the bottom and the y part of the model at the top. So y is continuous, u is binary. So it's like the parallel process model we looked at yesterday, but one part is binary, one part is continuous. We call the intercept growth factors IY for the continuous, IU for the binary, and the slope growth factors SY for the continuous and SU for the binary. And you can see that we're regressing all 4 of the growth factors on the variable, the covariate male, the time invariant covariate male. Okay, so we'll leave that there then. And as Bengt mentioned earlier, we have a lot of papers on the website that are available to you as PDF files, and there are a lot of applications of this 2-part growth modeling there that if you're interested in looking at them. So here's what the input looks like. So what is new here? If you go down to data 2 part, this shows you that particular function, which you can use while you're just to divide the variables and save them for further analysis, or you can actually use it while you're doing the analysis. And one thing I didn't mention when I was looking at the pointing over here is that the 2 parts don't have to follow the same growth function, and they don't have to have the same covariates. So although we're showing just a single covariate for both, and the same covariate for both parts, you can have different covariates predicting the continuous part and the different ones for the binary part. And for example, the continuous part might be quadratic and the binary part could be linear. So there's a lot of flexibility. And you might want, as a first step, to actually look at the continuous and binary parts separately in order to find the best fitting growth model for each part. Okay. All right. So data 2 part, the names option gives the names of the original variables. So m over 0 through m over 3. The binary option gives names that are going to be assigned to the binary part, and the continuous option gives names that are going to be assigned to the continuous part. And the names are statement in the variable command is only the names of the variables in the data set amp.dat. So the newly formed variables u0 through u3 and y0 through y3, they show up on the used variables list. It's in a way the data 2 part is like the define command, and these new variables have to appear after any of the older original variables. So the used variables list, we have male first because it's an original variable. It's named in the name statement of the variable command. And then u0 through u3 and y0 through y3 have to come after any original variables because they're new variables. Then we also have to use the categorical option to say that u0 through u3 are categorical binary variables. So data 2 part is convenient. It helps you, once again, not make a mistake in your logic in the define if you try to do it that way. So we're going to be using maximum likelihood estimation and numerical integration. The reason we need numerical integration is that when you have categorical outcomes and you have maximum likelihood and latent variables, then you're going to need one dimension of integration for each latent variable that involves categorical outcomes. Okay, so here's our model command. So we have a growth model for the binary part. IU and SU are the growth factors, and a growth factor for IY and SY, the continuous part. Remember the time, the measurement occasions were not equidistant, so we reflect that in the time scores of 0, 0.5, because this was from fall to spring, and then spring to spring would be 1.5, and then spring to spring again would be 2.5. So the distance between the measurement occasions is reflected in the time scores. And we are specifying a linear growth model for both of the processes. So once again, 0.5, 1.5, 2.5. And we're regressing all of the growth factors on male using the on statement. We're estimating, by default, all of the residual covariances would be free. So we're only, if we look at our path diagram, we can see that we're estimating the IY-SY residual covariance and the IU-SU residual covariance and IY and IU. So between the two intercept growth factors, across processes, and within process between the intercept and the slope growth factors. And because the default is to estimate all of them, we need to fix the ones we don't want to 0. And it's, you know, your decision which ones you want to estimate or not. So if you don't want them to be estimated, you say IU with SY at 0, SU with IY through SY at 0. So you can, any default in M+, if a parameter is fixed or free, the opposite can be done, providing that it doesn't make the model non-identified. Now, nothing new here except in the plot command. So we have two growth processes, and if in the plot command we want to plot both of those, you use the bar to separate the two growth processes. So series equals, we're saying U0 through U3, and in parentheses we say SU, so it takes the time scores for SU as the values on the x-axis, and then we say bar Y0 through Y3, and in parentheses SY, and it takes the time scores from SY for the values on the x-axis. So that's something that we didn't see yesterday, the plotting of two processes. Okay, so then we get our test of model fit, and because we're in this realm of categorical outcomes and maximum likelihood estimation, we don't get chi-square and the traditional fit statistics that you may be accustomed to, but we get a log likelihood value, and we also get AIC, BIC, and sample size adjusted BIC. Okay, so now here are our model results. So IU, SU, just to orient ourselves on male. So the binary part of the growth model comes first. And underneath that, we have the continuous part of the growth model. And if we look in the third column, we see that male has a significant relationship with the intercept growth factor for the binary part of the model, but not for the, it does not have a significant relationship with the slope growth factor for the binary part of the model. And we see that same pattern for the continuous. So and what it's saying here is that males are more likely to drink, and then they're more likely to drink more. So this would be the interpretation of that. If you look down here at the IU with IY, let's see, the two intercept growth factors, for the intercept growth factor for the binary part and the intercept growth factor for the continuous part, have a fairly high, a significant covariance. And this is possibly partly due to the fact that they come from the two parts of the variable come from one variable. So if you see that. Now I wanted to just remind ourselves of what we learned yesterday by recalling that the parameterization of the growth model for the binary part is going to be different from the parameterization for the continuous part. And we can see this by looking at the slide on the right here. We see that for the continuous part, the y variables, the intercepts are fixed at 0. And for that part, the y part, we have I, y, and sy being estimated, the mean, or the intercepts rather. But for the binary part, the thresholds are instead held equal, and only the slope intercept is estimated. The intercept, the binary intercept is fixed at 0, as we see here. So just to remind ourselves that we do use different parameterizations for the continuous versus the binary part. In this case with binary, had we instead let IU be free and fixed these thresholds to 0, the value 2.655 would show up where IU is. So the parameterizations are they're just different parameterizations. They don't change the results. And as I said yesterday, we do that for categorical and multiple indicator models because it puts less restrictions. Instead of fixing all the thresholds of an ordinal variable to 0, we can instead hold each threshold equal over time. And that's a less restrictive model. Now we have, oops. I'm going crazy. Okay, here we are. So here we have R squared. Now what's new here is that we have latent variables we're getting R squares for. So, and as you can see, they're not really large for the observed variables, but they're certainly larger than for the latent variables. And it is the case that it can be difficult, although we didn't try too hard with just one covariate male, but it can be difficult to find covariates that explain the variability in the growth factors. So that can be challenging. Now you remember that we have a conditional model. So that means that we're not going to get means, variances, and covariances from that model for our growth factors. So as we mentioned yesterday, we want to use Tech 4 for that. So if you ask for Tech 4, then you're going to get your estimated means for the 4 growth factors and your estimated variances here on the diagonal and covariances. So when you know, it's good to get into the habit when you're running an estimated model, or rather a conditional model, just ask for Tech 4, and then, you know, if you want to go back and see what the model estimated means are for this conditional model, you can take a look at that. We get lots of questions about that. You know, why did my mean go negative, you know, when I added a covariate to the model? So just remember that you're estimating with a conditional model an intercept, not a mean. Now, there's a paper here. It's called Beyond Multi-Level Regression Modeling. It's by Bankton, Tiamir, Asperahov, and I think the date is, I don't see the date here, Bank. Do you have it? Oh, here. Nope. Oh, it's a chapter that's coming out, but it's on our website. Okay, so it's by Bankton Tiamir. It's new. It's on the website, Beyond Multi-Level Regression Modeling. And what it did is, in this example, we have the same relationship between the covariates for both parts of the model, but it's certainly possible that that wouldn't happen. And what they did is they took a look at a model in the regular way. and they looked at the relationship. It was heavy drinking once again. And the result, if you just look at it as a one-part model, is that blacks drink less. But if you look at it as a two-part model, where you look at whether they drink at all, and if they drink, how much they drink, you see that, well, actually, I'm going to read it to you here, because I think they say it nicely in the paper. Consider as an example the covariate black. As is typically found, being black has a significant negative influence in the regular growth modeling, lowering the frequency of heavy drinking. So blacks drink less. In the two-part model, this covariate is insignificant for the continuous part and significant only for the binary part. This implies that holding other covariates constant, being black significantly lowers the risk of engaging in heavy drinking, but among blacks who are engaging in heavy drinking, there is no difference in the amount compared to other ethnic groups. So when you go to some of these models, you can get a lot more information out of your data. You know, your data can be allowed to tell you more. You can see more subtle relationships. So this is one of the reasons that we try to talk different models to you, so you use each one of them, but so you use one that may help you understand your data better. I think it's your turn.
And this is a model that seems to get popular among researchers. So I'll just add a little bit more on top of that, what Linda said. I should also mention that there's a paper on the website under the section of two-part modeling that concerns an intervention where the intervention has an impact on one of the two parts but not on the other. So you can get more nuanced intervention effects estimated. It's a paper by Brown and others, Eric Brown and others. Anyway, one key aspect here is that the two processes are correlated, not only by being influenced by the same covariate, but correlated, and they're quite strongly correlated. If you look at slide 33, you have a correlation between IU and IY on slide 33, that's 0.8. And that's also what Olsen and Schaefer found, which says that if your tendency, say that this is at the starting point, initial status, this is the tendency to engage in heavy drinking, that is, it influences the probability of engaging in heavy drinking. When that tendency to engage in heavy drinking is high, that person is also likely to drink a lot. So that makes sense from a substantive point of view. And those correlations can sometimes go up very close to 1. And we're not arguing that you should only correlate the intercepts. You can correlate all of them. We just try to keep the example simple. But the key correlations of the model, we would argue, are those three that are those three residual correlations that are shown there.